So I guess it's gonna good enough for me for the moment.
Oh, that's super long.
So bad.
Okay, that circle versus that circle over there.
Alright.
Okay.
So there was a question. Part should we just do one of the parts?
B and C. That's what I
Oh, B and C. Find an equation of the tangent line to the circle at the point 0, 0.
I just was like, I mean, I get it.
Yeah, so here's a line. So this just requires algebra 1 knowledge. This is the point 3, 4, and this is a tangent line to the circle at this point. Well, fact from geometry, every tangent to a circle is perpendicular to the radius drawn to the point of tangency. So this is a perpendicular, and then the slope of this line is 4/3. Yeah? Yeah. So therefore, the slope of this line, they're negative reciprocals of each other. Do you have some vague memory of this from Algebra 1 / Pre-Calc A? So this is negative 3/4, which looks about right. Therefore, the equation of this line is y equals negative 3/4 x. And then part C was just a more complicated version of the same thing, I guess, right? Find an equation of the tangent line of the circle at the point 6, 0. So here is now the point, oh no, it's basically really this, just about the same thing. There is the line 6, 0, and then again, this line is going to be perpendicular, so what is the slope of that? I'm guessing going down 4 and over 3, so the slope of this line is negative 4/3, and thus the slope of this line will be 3/4. And so if the slope is 3/4, then the line is y equals 3/4 x minus 6. That's pretty much all I have to do. All right, how about the calculus part of the homework?
Wait, what was the topic?
There were just a bunch of limit questions. I thought they were pretty easy.
Yeah.
Do we need to talk about them at all? I feel like we don't.
Wait, can we just, can I compare?
5, 4, 3, 2, 1, good. Can I have this homework?
27.
Put in a pile right here.
Oh, graphs. Oh, graphs is boring. Look at this. Look at this stuff.
Maybe like review stuff.
Always need spare time.
Wait, where?
Yeah,
No, if you make a function, you still have to follow the spare tire.
If I do like
It's supposed to have like
It's a lighter.
No, it really does, because like most of the games crash and not get taken off for it. It's really only for yourself.
About world.
Now, world, you actually have to like a formatted essay with like a topic sentence. It's ridiculous. But like other people agree, and you're like, if you have a topic sentence.
So, time for business.
I didn't watch it.
Time for business.
To grind.
Hi.
As an interception. Yeah, as an interception. It's really handy, but you're not even like this, and you have to
What are you talking about? What are you talking about? Pro Bowl? Okay.
T.Y. Hilton, he got the ball like.
Yeah. Cool.
Should watch it. Hey Mateo, Matt Ryan threw more touchdowns than Jimmy Graham.
What are you doing? All right, Sandeep, we're gonna start now. So, let's do a limit.
Are we taking notes?
Yeah, we're taking notes.
Okay.
So let's do a limit. Let's take the limit as, I don't know, x approaches 2 of 3x minus 1. Seems like a good. Okay, advanced limit. What is the answer?
5.
Yeah, when x gets really, really close to 2, this is going to get really, really close to 5. I feel like that's true. I'm going to make a graph of this. So, -1, 1, 2, 4, 5. Slope is 3. Also, I need an official note taker for this class. Who wants to do that this semester? Who did it last semester? You did it last semester? Are you willing to do it again, Kendall?
Yeah.
You sure? Okay, cool. So did you kind of start that already?
Yeah,
On the assumption?
I formatted my notes and
such a way that that would work.
Okay, awesome. I have to give you access to the thing, right?
Yeah.
Okay, cool. Alright, so I have a line, and here is my line. And just as you all suspected, as I get very close to 2, this function appears to be very close to 5. What I would like to explore now is what really, on a deep, low level, one means when one says that the limit is 5. So, and we kind of did something like this last semester. So Ron, I think that the limit as x approaches 2 of 3x minus 1 is 5. Can you be my skeptical adversary?
Okay.
Okay? Okay, so Rohan, the limit as x approaches 2 of 3x minus 1 is 5.
No.
No, seriously, Rohan, it's 5.
Prove it.
Exactly.
Say something like, what are you even talking about? What does that even mean?
What does that even mean?
Oh, I'm glad you asked. What that means is that when x gets very, very close to 2, the y values of this function get very, very close to 5.
Prove it.
No, Rohan, seriously. As x gets very, very close to 2, the y values get very, very close to 5.
How close?
Oh, good question. Okay, let's take it from the top. Rohan, taking it from the top. The limit as x approaches 2 of 3x minus 1 is 5.
What does that even mean?
What that means, I'm glad you asked. What that means is that as x gets very, very close to 2, this function gets very, very close to 5.
How close?
Oh, how close, he asks. Watch this, Rohan. As close as you want. Just like we did last semester, I have now turned the tables back on him. He asks me how close, I say, as close as you want. Okay, Rohan, let's take it from the top again. The limit as x approaches 2 of 3x minus 1 is 5.
What does that mean?
That means that as x gets very, very close to 2, the y values get very, very close to 5.
How close?
As close as you want.
5.
5. What is the meaning of that number 5? How about pick a smaller number? How about a smaller number?
0.5.
0.5. Haha! He's issuing me a challenge of 0.5. And what he is saying is, I say that the y values are getting very, very close to 5. He says, how close? I say, as close as you want. He says, well, how about 0.5? In other words, he wants me to get 0.5 close. In other words, he is challenging me. He is challenging me to be within 0.5 of the number which I am claiming the y values are getting very, very close to. Okay, so what we can do geometrically to draw a picture of this situation is to call this 5.5 and call this 4.5, or maybe we should just do it like this. So like 5 plus a half and 5 minus a half. And so certainly it's true that if I claim that the values are getting really, really close to 5, then they should be able to get within a half of 5. So he issues me this challenge. Remember, it's like a game. This is called the Qualifier Game. I say they're getting close. He says, how close? I say, as close as you want. He says, 1/2. Now it is my job now it's on me, right? It's my turn. I have the mic. How do I respond?
Make an excellent.
No, you can't drop the mic until you win the argument. First you have to win the argument, then you drop the mic.
And then do.
Yeah, so what do I do? What must I, this is a little bit different than what we did last semester, so you actually have to be thinking now. What must I do, just using common sense, what must I do to meet his demand?
Give him a point on that line.
5, 2. Do a proof.
Do a proof. Okay, wait. Hold on. Remember, I'm claiming that when x is very, very close to 2, that the y values will be as close to 5 as anyone might want. He says 1/2, and now I have to respond. How should I frame my response? Not yet with the proof, just a Sandeep.
You have to prove that there's like a bunch of points within 1/2 above and below 5.
I have to show that there are a bunch of points within 1/2 of 5. Can you be more specific
Well,
about what exactly you're saying?
like, cause like last semester we did this thing where it was like you have to prove that there's like an infinite amount, or like.
Yeah, I know I did last semester, but I'm trying to get you to think of new. But I'm fine with that hand.
I don't know, but you could do the same thing on the 2.
Yeah. Can you give me some words there? Do the same thing on the 2. Like, what do you mean?
Like 2 plus half, 2 minus half.
Okay, so she says let's do 2 plus 1/2 and 2 minus 1/2. Does that work? I don't even know. She hasn't actually even said yet what it's supposed to do, but already you guys are saying it doesn't work. Those of you who think it doesn't work, what are you talking about?
Exactly.
Trying to find a range of x values that make it within 0.5 of 5. Make the y value within 0.5 of 5.
Yeah, okay, that was some words. We finally got some words. Yeah, Mateo says what you're trying to do is to find some what'd you say? Some set of x values or some interval of x values such that when I plug them into the function, they will land in between the parallel lines like they're supposed to. So, does 2.5 work? No, it seems like not. How do you know that it doesn't work? Without actually like doing arithmetic, how can you just kind of like feel it?
Because the slope is 3.
Because the slope is 3. So if the slope is 3, what maybe should we be doing? What numbers, how far away from 2 can I go in order to ensure that when I plug those numbers back into the function, I land within the challenge set by me? Everybody who gets it.
1/6 as far away.
1/3 as far away, which is 1/6,
I
yeah.
thought we weren't supposed to do arithmetic.
Oh, I don't know. Oh, yeah, okay. There's some arithmetic. Yeah, so it seems like it's not algebra, it's just like common sense, right? Yeah, so, 1/6. 1/6 works. Do you guys see that now? If you didn't a minute ago, you should now. The slope of this line is 3, so therefore using common sense I see, well, if the slope is 3, then I'm allowed to inch out by 1/6, and when I plug it into the function, that 1/6 x interval will get converted into a 1/2 y interval. Give me some vigorous head nods if you're with me. Eric, you with me? Yeah, and in fact, this is how the game works. Rohan, I say that the values get very, very close to 5. You say, how close? I say, as close as you want. You challenge me with a single number, 1/2, and then my retort to you is 1/6. And 1/6 is a so I win this round, right? I win this round because I win the challenge. I've told you precisely how close to 2 I must get in order for my y values to be within 1/2. Do you guys see how this works? Okay, Ron, give me a different challenge.
1/3.
1/3. He's really stepping it up now. So now he is, and I don't even have to change my picture. So now he's saying, well, you handled 1/2 just fine. I dare you to handle 1/3. Can you possibly get within 1/3 of 5? Well, now I think I can. I need to change my retort to him. What's my new retort?
Minus 1.
Yeah, now my new retort is 1/9. And when I say 1/9 in this context, you know that what I'm saying is how close to 2 or how far away from 2 I'm allowed to go such that this is true. Do you guys get this?
Yeah.
All right, and so if the limit is truly 5, then I must be able to produce such a retort for any possible challenge. So, yes, Yo.
What if I challenge 0?
For any possible non-positive, non-zero challenge whatsoever, I must have a retort.
Non-positive?
No, for every, what'd I say? For every non-zero positive number challenge whatsoever, there must be a positive non-zero, that's redundant, there must be a positive number retort available to me. And remember how we talked about this last semester? It's like there are a, did we have this conversation? How, like I'm up on stage, I'm the defender, it's like some kind of weird math open mic night. I'm up on stage, or like stand up or something, right? I'm up on stage, and I think that the limit is 5, and you are the crowd of angry villagers with pitchforks and. Did we talk about this? I feel like we did. Maybe in some periods only. You're the crowd of angry Villagers, you waited in a long line in the rain. It was overpriced admission to the math open mic night. You have pitchforks, torches, maybe even other things. And you are angry. Maybe you're hungry. I don't know. What else can we add to this? And tired, yeah. Done too much homework, sleep deprived. Wow, we're getting, this is like the teenage id is pouring out into this story. So parents don't understand me. So now, I think that the limit is 5, and it's your job to be a skeptical yet rational audience. So you're quite polite. You're angry, but you're quite polite, and you are challenging me with certain numbers. And with every person in the room, I meet that challenge. Then someone else says, no, what about me now? What about 1/100th? What about 1/1000th? Okay. All right, we have a name for this number. This number is epsilon, the Greek letter epsilon. And epsilon is often used to refer to tiny numbers. So we let epsilon is the challenge, and my response is delta, another Greek letter, and lowercase deltas look something like that. Okay, so for any possible epsilon whatsoever, I must be able to respond with a delta. All right, so here is this. So yes.
What if, because I'm an angry villager and I'm sarcastic, what if I say like 1,000,000?
Yeah, I should be able to have a response to that too.
For like any graph? Or it has a...
Yeah, it can get a little complicated, but yes, I must, for any number, I must have a response. But if you give me some ridiculous number like 1,000,000, I can just say like 1. That'll be good enough, you know, right? Because it's easy. The bigger your number, the less difficult it is for me. So sometimes you might come up with some fancy formula where you say, well, if someone says something silly like epsilon bigger than 2, then I'll just say 1. But if they say something reasonable, then I'll have a formula for it. Anyway, that's a more advanced thing. I think we're ready to actually do this. So here is my claim. My claim is that the limit, as x approaches a, of some function in general is L. If and only if, and what we're going to do is we're going to write out the formal definition of a limit. First, let's make the picture.
I already did that in my notes.
You already did this in your notes? Oh, great. So the formal definition. Oh, so the picture. So here's generic function. Here is some point A, and when I plug in A, I get L. I think. So this limit is L if, for any possible epsilon whatsoever, so for any possible challenge, any which we think of as being any tiny number that is a challenge to me, a demand for me to be quite close to L, as I'm claiming happens, then I must be able to respond with a delta. And the delta refers to how far I'm allowed to go away from A, such that these values, when plugged into the function, lie between the parallel lines. Everybody get it? Okay, now let's just write this out in words. So let's do it. Somebody, talk to me.
Something is less than epsilon. Epsilon is greater than...
For every epsilon greater than 0, there's...
For every, yeah. So for every epsilon greater than 0, I told you that those are the rules of the game, that epsilon has to be a non-zero number. For every epsilon greater than 0,
there exists an n.
yeah, but the n is gone now, right? We don't have n's anymore. There exists a delta, yeah. There exists a delta greater than 0, such that what's true about that delta, which I have chosen,
A minus delta, well, f of A minus delta, f of A is like L.
she wants me to write f of A minus delta, but you know what?
Plus or minus.
That's not good enough, because it's not good enough it's not good enough when I plug in that point A minus delta. It's not good enough if that lands between the parallel lines. What actually must be true is that all of the x values on this interval.
Less than is, well, there's
The range.
like
So I need to say something a little bit more right. Right angled brackets. Wait,
F
what?
of A minus the comma. A plus, like this.
This is in a rule.
Yeah, for any x in that interval, right? So yeah, so what has to be true is that for any x, for any x, if yeah, if x is somewhere here, so if x is between a minus delta and a plus delta, then
F of x and then the interval.
yeah, you take any number whatsoever in this interval, then when you plug it into the function, your answer lies somewhere between L minus epsilon and L plus epsilon. This is hopefully this should match up exactly with what we've been talking about, right? Give me any x value in that little interval around A, then when you plug that x value into the function, you get something which lands between the parallel lines. All right, this is 98% perfect. There's one tiny problem with this. Yeah.
The greater than, well, never mind.
Almost 100% correct. Okay, here we go. I'm pretty much telling you now. Is that limit still L?
Oh.
Yes, right? Because remember, when we say the limit is L, we are talking about values near A, never values at A. What the function's doing at A is irrelevant to us. So I need to say a little something, yeah, like, sorry, she didn't raise her hand, but she just said the right answer, that, yeah, for any x in this interval not counting A, right? I make no claim about what happens at A. What? No space. Oh, don't cry. Okay, so this is great, but we are fancy, and since we are fancy, we can write this in a more compact way with symbols and like stuff. So let's do that now also. We can use the quantifiers, so we can say, for all epsilon greater than 0, there exists a delta greater than 0, such that for any x whatsoever, this conditional holds. And this conditional can actually be more succinctly phrased in terms of absolute values. So if x is between a minus delta and a plus delta, I can sort of say that a little bit cooler. I mean, is anyone?
Yeah, I remember.
Yeah.
The
absolute value.
absolute, yeah, the absolute value.
Of what?
Of that.
The absolute value of x minus a is greater than 0 and less than delta.
Yes. Yes, he said two things there. First of all, this absolute value of x minus a is less than delta. Where did he get that from? Let's see. This is, the way you should read this is, the absolute value of x minus a is the difference between x and a. So if the difference between x and a is less than delta, in other words, the gap between x and a is smaller than delta, so that's kind of right, then what's true? What should be true?
Then f of x. I mean, no, then
F of x,
L minus L.
Yeah,
L minus the absolute value.
Yeah, then the gap between the value of the function and the number you're claiming to be the limit should be less than any number whatsoever which you proposed. And the way we handle that little technicality, which Rabbi Fleischman also said, is when we throw a little 0 in here, see this little thing I just added? That takes care of the x is not a case, because by demanding that the distance between x and a be positive as opposed to 0, then that means that this conditional, the antecedent of this conditional doesn't refer to x being a at all. You guys with me? So this is sort of saying if x is, if the distance between x and a is less than delta, but x is not equal to a itself, then the distance between f and l is less than delta. Okay, congratulations. This is the formal definition of a limit. Formal definition of a limit. And other people call this the epsilon delta definition of a limit. And yeah, so there it is. All right, and let's see, what do we have to say about this? So many things. Arun, how much of logic should we tell them? Like a lot, or just some?
Oh, you mean for like?
Yeah, so there's a whole class in this high school called logic. in which we explore the history of math, especially the history of the 19th century, and we learn all about this. But for now, maybe I'll give you a little taste.
No.
No? You don't want a taste?
Is it a good class?
The best
It's like
class.
it's like
At
a
least second to this class.
second. Whoa. No,
Actually,
Baton
probably
Rouge's
better.
2 favorite classes. All right, okay, I'm just kidding. All right. Yeah. So here's the thing. How much did I tell you guys last class? I told you that basically Newton invented calculus, right? Did I talk about Leibniz at all?
No.
About who? About what?
Gottfried Leibniz,
Oh.
German philosopher in the same generation as Newton, kind of also invents calculus. All right, this is actually complicated. Rohan, this is complicated. As I mentioned, Newton invented calculus to solve physics problems. But he was kind of crazy. And nowadays, anytime you do anything even slightly cool, you tell as many people as you possibly can about it, pretty much like within the hour. And if you discover some new math, you better very, very quickly publish it, because someone might like steal it from you or something, or someone else might be working on the same thing at the same time. And you want to get rich and famous as soon as possible, just like I'm going to be with this video series. All right. So Newton, on the other hand, was crazy. Also, was a long time ago. So instead he discovers calculus. Instead of actually telling people about it, he just holds it as a giant secret for 30 years. Doesn't tell anybody. And again, I think I'm kind of screwing with the historical record a little bit, so fact checkers, send me an email. But generally speaking, my vague understanding of my memory of this third hand is that basically he discovers calculus. He uses calculus to prove all these physics theorems. He publishes whole books, and he publishes whole books with these physics theorems in them, which require calculus. Yet he doesn't show his actual work.
Why?
He just does. He's just crazy because he's just a crazy, paranoid, crazy guy. I guess he's boss. Yes, if that's your reason. If that makes sense to you, then yes. So he doesn't do this, and actually he is basically just plays like a 30-year game of like na. I have calculus and you don't. Even going so far as to like pose problems that he knows require calculus to solve, and just watching people just wait and just suffer and not be able to do them. So then he waits long enough that eventually someone else discovers calculus. Basically 30 years later. Newton is English. So Leibniz is a German philosopher. He had totally different motivations, in my understanding, for calculus. He was some sort of philosopher investigating the very nature of change, and this led him to an analysis of like what infinitely small change actually means, and thus he discovers calculus. He publishes it pretty much right away. Newton immediately accuses him of
Stealing.
yeah, what's that word?
Really?
Yeah, of plagiarism. And Newton then produces this giant pile of like books of his last 30 years, like journals, saying, "Oh, I've been doing this for 30 years." So, okay,
So if you keep
questionable.
it under wraps, like
Why would you do that? Right.
Wait,
Exactly.
steal your work,
So Europe erupts into controversy. Generally speaking, the English kind of world and the continental Europe were sort of very different culturally. All of the kind of German and French continental European mathematical establishment backs Leibniz and thinks Newton is a crackpot. The English people believe that in fact Leibniz has plagiarized calculus from Newton, and Newton basically says, "How could you possibly have come up with this yourself? Only I'm smart enough to do this." And basically, it's never solved. It's extremely bitter, and this dispute goes on for the remainder of both their lives. And in fact, it really isn't until like 100 years later, after they're both long dead, that documentation emerges, and the historical consensus is that they did discover it independently. Newton first, Leibniz second, but independently, so they are considered co-creators of calculus. Okay, not to mention the fact that like many of the things were already done by other people. Newton and Leibniz were the two that kind of pulled it all together. Did you have a quick question?
A little bit. The best part of the story is Leibniz gave like Newton like 10 years to actually just like publish all of his work. He was like, "Hey Newton, I know you found this thing. You should publish it because this is a pretty big deal." And Newton was like, "No, go away."
Yeah.
For 10 years. And then when Leibniz published it, he was like, "You plagiarized me. What were you doing?"
Yeah. The whole thing doesn't make Newton look good.
He's a jerk.
So, he's kind of a jerk, yeah.
He has like these laws, so we sort of.
Yeah, he has lots of laws. We have to study him forever. Good. So, what was the point? Oh yeah, this is actually going to come up in this class a couple times because due to the like 100 years which elapses in which you are either like on Team Leibniz or like Team Newton, basically different notations emerge. They use completely different notations, and in fact, you will find in this class pretty soon that there are just it's like some people are like, Mr. Rose, why are there 5 different ways of saying the exact same thing? It seems like for every calculus thing, and part of the reason is because there's like the Newton notation and there's the Leibniz notation, and we sort of use them all the time, and they both became kind of dominant because they were both dominant in 2 different parts of Europe. Interestingly, Newton, though all of calculus is based on limits, didn't really talk about limits at all. And in fact, what you will learn when you read logic math is that Newton and his entire generation and the subsequent basically 150 years of mathematicians, while they were doing calculus, they were just totally winging it. They had no idea what they were doing. Newton was just a genius, and what geniuses do is they just go with it. They just hope for the best, they use their intuition, they just feel out what they think is right, and they just push on forward, whether it really makes sense or not. And some of that stuff that we were talking about last class, remember how we had that very brief conversation where we're like, oh, instantaneous velocity, speed at x equals 3, what does that even mean? It's like, because it's like 0 over 0, it doesn't even make any sense. These kinds of fundamental understanding of what actually they were talking about was like elusive. And went on for a really, really long time. All right, fast forward like basically 200 years to like 1820 or so, things are a mess. Slowly, little by little, as calculus advances, the fact that the foundations of calculus are so wishy-washy becomes more and more of a problem. People start to panic that they actually don't really understand what they're doing at all. And so eventually there's the need to fix things up. And there is a new generation. Some of these people are up on this board. There is Bernard Bolzano, who is a Czech, famous Czech mathematician. The other one who's really important, who is somehow, he must have fallen off the wall, is Cauchy. Cauchy, really, really important French guy. And maybe most importantly, Karl Weierstrass, German mathematician. These 3 guys, but also many others, over a period of about 40 years, from about maybe 1820 to 1870, totally fixed calculus. And when I say fix, what they do is they really get in there and they make it much, much more precise. Instead of like doing calculus proofs via just drawing some picture and being like, yeah, you know, you kind of see like there's a tangent line, and now I'm saying like intentionally to show you the looseness of Newton and his definitions. What Weierstrass says, no, we will not do that. We will have everything very, very precisely defined. And so this definition of a limit is historically emerges 200 years after Newton. This is the kind of Weierstraussian definition of what a limit means, and we are living in the shadow of this sort of revolution in mathematics in the 19th century. And this is very kind of like advanced and fancy, right? So this is now in calculus classrooms all across the country or all across the world. When you learn about limits, you learn hopefully this formal, precise definition of what a limit means. This didn't just come out of nowhere. This came. I guess this came. The thing I'm trying to get across is that this came as a result of hundreds of years of sort of careful examination as to what was really